Good morning, students.
Good morning, sir.
Thank you. Okay. So, yesterday, up to what point we have covered? Can anyone let me know? I think this third problem we have solved, okay, in conventional method, but we have not solved it in ES. Am I right? Or I have completed that also? No idea?
Yes, sir, you had done conventional, but not on ES.
Not on ES, right? Okay. So, anyone solved this in the ES? If anyone has done this, then send me the code in mail, then I'll paste it over here. Or you can paste over there in our Teams itself. Can anyone tell otherwise step by step? What can we do? T1, how much is it? 15 megapascal means, okay, 15 and 100, 1500. Okay, then T1 equal to, then 600. And then what data given? M1 equal to 100 kg. Okay, so let us put this also. And then P2 equal to 2 megapascal. Actually, this should be 15 megapascal means 150 power. Then multiplying with 100, then 15,000 it should be, yes. Okay, this is 2 megapascals means 20 bar and multiplying by 100. Okay, fine. Then its temperature is 350. Okay, then T2 equal to 350. Fine. And then M2 equal to 20. Okay. And M3 equal to M1 minus M2. Fine. And then P3 is given. P3 equal to, and then 75 kilopascal. It's already given in the kilopascal. So this simply 75. Okay. And X3 is given to you, that is 0.95. Is it? Then what you need to calculate? You need to calculate total work output from this particular turbine. Yes. Then in that case, workout means what we have seen in this particular energy equation. Okay. Then we have to calculate enthalpy of 1 equal to work output plus enthalpy of 2. Is it? Okay. Along with mass multiplications. Yes. Enthalpy of 1 multiplying by inlet 1 equal to work output. Okay. Plus enthalpy going in this particular tapping location and enthalpy coming out as the outlet of the turbine. Okay. This is the formula we have to consider. Fine. Then here we need to find out H1, H2, H3. H1 actually direct from the properties. Let us write that also. H1 equal to enthalpy. This is the steam, right? Yes, steam. Steam. E1 equal to P1 equal to T1. Fine. Okay. H2 also same. H2, let us copy this. T2. Fine. Then what about H3? H3 is actually not any saturated liquid or saturated vapor. H3 is with certain dryness fraction. Yes. So what we need to calculate over here? HF, saturated vapor enthalpy, sorry, saturated liquid enthalpy, we have to calculate, and saturated vapor enthalpy. Okay, we have to calculate. Then we can get this. Okay, then let us do that. HL3 equal to enthalpy. Okay, steam equal to P3 comma X0. Okay, that is HL3. Now similar fashion, HG means enthalpy of saturated vapor. Okay, here this is 1. Fine. Okay, then those we are finding out. Then H3 would be HL3 plus X3 multiplying H minus HL3. Is it? Fine. So all enthalpies we have calculated, H1, H2 here and H3 here. Now what we need to do? So after setting this equation appropriately, then it is coming out like this. Yes, this thing. Okay. The turbine equal to M1 multiplying H1. Yes. Then this is H2, M2, H2. Okay. This is M3, this is H3. Is it? So I am running program. I think I have done everything. Okay. So what it is telling about. Okay. Here we have done a small mistake. It should be ENTHA. TK. Okay. So then what we have done? Work output is 91.565 megawatts here. Our units are here in the kilojoules. Yes, sir. Are kilowatts. That is the reason we are getting here 91680. And all the enthalpies and all are given in this particular table. Okay. M3 is 80 and H1 3582 it should come. 3583 here and H2 3137. This is 3138. Okay. And H3 is here. Yes, sir. 2549. This is 2549. Okay. And along with that, to calculate this H3, we have calculated saturated vapor enthalpy, saturated liquid enthalpy. Okay. This is anyhow our input only. Once we have done this, and only the value we are requesting over here in the calculation table, that is turbine work. Okay. This is the turbine work we have applied. Okay. This code anyhow I will give you. Anyhow, this tutorial will be completed in this class only. After the class, immediately I will paste this tutorial and all 5 codes. Okay. Now let's go this problem number 4. Okay. Please read the problem. Okay. And try to solve it. Today we have sufficient time. We have 2 more problems only, not many. Okay. So please solve it by yourself. If anybody will be telling this particular answer, I would be very happy. So in this particular tutorial, I think you might have observed, okay, all the components we are covering over here. That means the how to implement energy equation, means first law of thermodynamics energy equation and the control volume of each component like turbine and throttle valve, okay, and compressor. Yes, these all we have seen. The problem number 4 is about heat exchanger. Okay, about heat exchanger. What terms would be ignored, what terms should be considered. Okay, these are all the things we have seen in different components. Okay, here also please form this energy equation for this heat exchanger like this. This is your heat exchanger over here. Okay, and then if you tell me what are the terms are ignored and what are the terms we are considering, okay, I would be happy. I am waiting for your response.
It is coming around
Yeah.
70.
Flow rate of the cooling water. Yeah, 70. Yeah, yeah,
Approx 70.
exactly. 69 point something it is. Okay, nice, nice. Thank you. Okay. Okay, so let us start after 1 minute. I think some other students also trying to solve it. Okay, so this problem is about at the beginning in the first class itself, we have discussed thermal power plant, how it operates. What we are using there, which cycle? Rankine cycle. I hope you remember. In the Rankine cycle, constant pressure heat addition is happening in the boiler. Okay. Then steam is reaching to the superheated state. Then that superheated steam will be impinging upon sorry, on the steam turbine. Then steam turbine is generating the work. Okay. Then the process in case of steam turbine, that is isentropic process, that means entropy constant process. Okay, adiabatic expansion process, that is actually. Let us see when entropy comes up, that time let us see. Then at the exit of the turbine, condenser is connected. Okay, so what condenser is doing? It's changing the phase, whatever the steam coming out from the turbine, it's changing the phase. Then that saturated liquid is again pumping back to the boiler. There again we need pump that we have seen at the beginning. Okay, so this is the component condenser. Okay, this is the component condenser. So how the condenser is working here means, this is actually steam. Here actually water brings water. It has mentioned here water. Okay, but it is at this particular 10 kilopascal pressure and such a high temperature, it won't be actually water. It is the gas itself, means vapor itself. That is the reason this vapor is coming up here as the saturated liquid. Yes. Okay. So this is the vapor state. Here pressure is maintaining constant. Okay. Saturated liquid at 10 kilopascal and vapor at 10 kilopascals. Yes. So this phase change is happening. Phase change, how the phase change will be happening? Whatever the latent heat of energy involved at this particular pressure, that much of energy should be removed or subtracted. Okay. So how would you remove this latent heat of energy? Certain other fluid should be taking it and carry away. Okay. Certain other fluid should be interacting and taking it and carrying away. But the fluid should not be mixed with this. The condition is fluid should not be mixed with this. Okay. So that is the reason. This is the heat exchanger. Okay. Here in the problem itself, it is mentioned by lake water. Okay. So that means this is operating at atmospheric pressure only. Okay. When you compare with this thing, this pressure is low pressure and this is at high pressure. Okay. And this water, whatever is coming from the lake, is 20 degrees centigrade and it is taking the heat from the steam. Okay. Because of that, this water reaches to the 30 degrees centigrade. Okay. That means here the person asked you to calculate what is the mass flow rate of this to achieve this particular condition. Okay, so this is simply no work involved in this, and we are considering this is the steady state process. Yes, this is your energy equation over here. Okay, so this is the steady state process. That's what this term is 0. Then we have our equation like this. Then we are ignoring these potential energy terms as well as kinetic energy terms. Okay, and when you consider this is the closed system. Okay, the closed system means this is your control volume. Sorry, this when you are considering this is your control volume. Okay, the heat loss from the control volume is 0. Anyhow, nothing is there here to generate the work. Okay, so what is remaining over here? Only the playing with enthalpies. Okay, apart from these enthalpies, all the terms would be 0. Okay, so that is the reason what we are considering. This is the cool water and enthalpy of at this particular location plus this is, that means enthalpy inlets equal to enthalpy outlets. We have equalized simply. Okay, this is the stream coming over here. This is the stream coming over here. If you observe over here, the flow is in opposite direction. Okay, the flow is opposite direction. Based upon that particular phenomena, actually these heat exchangers are classified in different ways. Okay, this heat exchanger we can call it as counterflow heat exchanger. Those all anyhow you will be learning in next semester in the heat transfer. Okay, fine. This is the counterflow type of heat exchanger. What are we doing over here? Enthalpy inlet to the control volume equal to enthalpy outlet from the control volume, that we are doing over here overall. Okay, this is the enthalpy carrying by cold water. This is the enthalpy carrying by steam. This is the enthalpy taking out by cold water. This is the enthalpy, rest of the enthalpy in our saturated liquid. Then what we need to do over here? Anyhow, we have to calculate this cold water mass flow rate. Yes. Then this steam mass flow rate we know 1 kg. Okay. And then we need to calculate enthalpies over here. Okay. That is the thing. From the table, okay, the liquid enthalpy, it is here like this. H20, H30 means 20 at 20 degrees, at 30 degrees. The pressure is same. Okay. So from the data table we have taken this. And for case of the steam at 300 degrees centigrade and the pressure of 10 kilopascal, this is its enthalpy. Okay. And saturated liquid at the same pressure, it is its enthalpy. Okay. And this is after rearranging these all, this particular equation. Okay. You can get like this. Now we know all the values. Okay. Enthalpies as well as mass flow rate of the steam. Once you substitute everything, you will get 69 kgs. Okay, fine. So then, shall we solve this problem in our this thing? Yes. Let's try. Let us try. These all are very simple actually. Nothing. Okay. So I'm removing this, deleting this. Okay. Then what shall we do over here? P P, let us consider hot side. Let us consider this is the hot fluid, this is the cold fluid. Okay. So let us consider P hot 1 means that is the inlet is 10 kilopascal. Directly in kilopascal it is given. P hot 2 means that is outlet equal to how much can we consider? This is same, right? Pressure is same. We no need to consider it again. Okay, no problem. Anyhow, let us consider. Okay, then T hot 1 equal to 300. Okay, and Anyhow, this is the saturation liquid only, so temperature also would be same. Okay, then what is the water condition? Water condition, pressure of cold. Okay, equal to 100, it is considered. Okay, inlet. Even pressure is same actually for both the cases, means inlet outlet. It's happening constant pressure. Both hot fluid is moving at constant pressure, cold fluid is also moving at constant pressure. Only temperatures are matter here. Temperature of cold fluid 1 equal to 20. Temperature of cold fluid 2 equal to 30. Fine. Then M1 equal to, let us consider M hot fluid. Okay, equal to how much? 1 kg they have given. Okay. So then enthalpy of cold fluid at 1 means inlet, or otherwise enthalpy of hot fluid outlet can we calculate. Enthalpy of hot fluid at 1 equal to enthalpy in, okay, P equal to P hot fluid 1, T equal to T hot fluid 1. Okay, fine. Yeah. Enthalpy of this at exit. This we can consider hot fluid 2. Okay, pressure is same, obviously, pressure is not changing. Okay, and instead of considering temperature over here, exit temperature is same temperature. Okay, but pressure is same, temperature is also same. Only thing what is happening, phase change is happening. Why? Because latent heat you are subtracting. So here you need another parameter over here. Yes. Okay, independent variable you need over here. So what can we give? We can give simply x equal to 0. Is it? That means at this particular pressure, its dryness fraction is 0, means it is completely liquid stage. Fine. Two enthalpies we have calculated. Now enthalpy of cold inlet. Okay. Equal to 30. Okay. Okay. And then equal to equal. Okay. Here T equal to, but here also pressure is same. Okay, that way what we have calculated, both the enthalpies we have calculated. Fine. Only thing is we just need to write this particular formula, otherwise nothing. Okay, very simple when you do this in engineering equation solver. But however, you should have idea about all formulas, all equations and everything. This is like calculator come readily available data for you, nothing more. EES means it is a calculator, but you no need to press every button upon the calculator itself, it will be doing. Okay, once you rearrange the formula and data is readily available with you if you write in this kind of syntax. Okay, and then M cold. Okay, M Okay, so done. All the data given, enthalpy is calculated, and mass we are calculating. Let me run and see. Where is this guy? The table. Okay, here. Okay, so this is it giving you 68.99 kg. Yes, sir. Okay. Here actually data we are asking in terms of the table actually. 1 million, let us put here 2 otherwise. I should be confused. Okay. Okay. So this is amount of water required 68.99. That means 69 kgs we have taken. Okay. Fine. Very fine. This is about problem number 4. Problem number 5 is actually very interesting. Okay. So reading itself would be taking even 3-4 minutes. Okay. So please read it very carefully. Okay. Once you read it and understand yourself. Okay. And also analyze this particular circuit. Okay. In the electrical language, we should say circuit as of now. Otherwise, the schematic line diagram. This is in mechanical terminology, schematic line diagram. Okay. So simultaneously analyze this schematic line diagram. क्लास में हूँ।
साइन कराने आया था।
11 से 12 एक क्लास है, 12 से 1 बजे दूसरा क्लास है।
मेरा भी क्लास है।
वो तो आपको क्लास है ना, तो प्रॉब्लम नहीं।
मैं कल जस्ट साइन कराने के लिए आया था।
Okay, so this is a typical nuclear thermal power plant. In case of the nuclear plant, that is only replacement of energy source, nothing more. Even though this is a nuclear plant, in conventional thermal power plant, we burn coal to generate the heat. Okay, that heat is using for producing the steam. Here, instead of the coal, we will be using a reactor, okay, nuclear reactor. Those reactors are like pressurized water reactor, okay, and fast breeder reactor, which is fast breeder reactor is like Indian technology actually to say, okay. So these kind of different nuclear reactors are there. In the nuclear reactor, there is uranium fission reaction is happening, that is generating so much of energy, heat energy. That heat energy we are using to generate the steam. Okay, that is only the nuclear reactor is only the heat source. Anyhow, once steam is there, that steam will be impinging upon in practical scenario, impinging upon the low pressure turbine and high pressure turbine. Okay, this is the high pressure turbine. Whatever the steam is coming up, that will be reheating. Different processes are there. What is the reheating, regeneration? These two equipments are there, reheating and regeneration. That anyhow it is there in our syllabus. We will be learning that in cycles chapter, where we will be discussing about Rankine power cycle. Okay. So here we just need to focus upon this thing only. This is that see. You need to find out what are there. A, moisture after the separator here, okay, and B, power output from the low pressure turbine, and C, power output from the high pressure turbine, okay. Anyhow, total power output from the total system, that is summation of these two only, nothing more. Here actually we no need to run our this thing, what is that, engineering equation solver. Why? Because in the table itself here all the data is given, enthalpies are given over here, okay. So there is no role of ES over here apart from using like the calculator that you can use anyhow, okay. You no need to find out the properties itself are given over here, okay. What is the pressure, what is the mass flow rate, what is the temperature, respective enthalpy is also given over here. Let us directly go to the problem. This is the thing we are doing, okay. This part we have taken, okay. This part we have taken over here. This is, and then let us start from A, okay. So A is about this thing, this part again, okay. How can we write our equation? This is one inlet, here you have two outlets, okay. One inlet, two outlets. This is just moisture separator. What we are considering over here in this control volume, there is no heat transfer, okay. That's what Q term in our energy equation, 0. And this is not the device which is generating or producing work. These are producing work over here, okay. That is the reason here work term also gone. And then this is the steady state process. That's what dE by dt, okay. That term also gone, okay. And what is remaining over here? Anyhow, we are considering potential energy terms and kinetic energy terms from the beginning. For the thermodynamics point of view, we are neglecting them, okay. As like your previous problem of heat exchangers, this is same kind of heat exchanger, okay. But otherwise actually mass separation is there over here, okay. That is there, not heat exchanger. Obviously this is not heat exchanger, this is the mass separation is happening over there, okay. So that's what enthalpy at the inlet equal to enthalpies at the outlet, summation of these two. What we need to do over here, mass we know, the mass is M3, M4, M9 given in the table over here, okay. M3, this is 62.8, M4, okay, that we may need to calculate, that itself is your this problem. And what is that? M4, M9, M9 mass is given, okay. This is the equation, okay. Anyhow, M3, M9 we know, okay. Then M3 equal to like this, M4 plus M9, then you can calculate M4 over here, okay. The only thing is H4 you have to calculate. This data also, Okay, what is this data? H3 and even H9 given in your table. Okay, simply we are calculating H4. This is only thing is you need to analyze this particular problem over here. Okay, you need to understand what is happening over here. Otherwise, problem solving is not much difficult. Okay, this is the H4 we have calculated. However, this H4, okay, once you check this H4 at this particular pressure and the particular temperature, okay, this particular pressure of 350 kilopascal, okay, so maybe this less than what we can say, less than the saturated vapor enthalpy. Okay, if it is less than the saturated vapor enthalpy, what can we decide over here? That itself has certain dryness fraction. Okay, along with this enthalpy, we have to calculate dryness fraction also. So whatever the operating pressure is there, that 350 whatever kilopascal, at that particular pressure, we have identified from your table these enthalpies. Okay, this is the latent heat, this is liquid enthalpy. Okay, from that we will be calculating our X4. Okay, this is it's means whatever is the possible dryness fraction is means moisture content is there. That moisture is separated by channel 9. Okay, and still certain moisture is there. That is 0.9755 dryness fraction. Very little moisture is there. Why moisture should be avoided? Okay, and up to what level of moisture we can expand in the turbine? These all let us see in further chapters. This is about A. B. B is about calculate turbine in means energy in low pressure turbine. This is your low pressure turbine. What is happening over here? This is 4 mass multiplying by enthalpy at the 4 is entering inside. That is okay. Then obviously output would be mass multiplying by enthalpy at 5. This is that, and certain amount is going in between over here. Okay, where it is going? If you go back, you can see over here. Okay, this is okay. Certain steam itself is tapping and giving over here. Okay. Why should we tap in between? Those are, let us see in your power cycles. Okay. So that's what this enthalpy multiplying the mass and finally work output. This inlet enthalpy equal to outlet enthalpies per plus work output. That is the formula over here, energy balance equation. Okay. Then like this way, H4 we know, just now we have calculated. Okay, H4 and H5 and H8 we can get from the table itself. We no need to go data tables actually. In the problem itself they have given H5 and H8. H5 it is given over here. Okay, and H8 it is given over here. Okay, then we are calculating here our work. Simply this is the work. Okay, in the similar fashion we are calculating high pressure turbine, means this is the high pressure turbine. What is happening over here? This is the mass at 2 multiplying by its enthalpy. Okay, equal to mass multiplying by enthalpy at 17, mass multiplying by enthalpy at 12, mass multiplying by enthalpy at 3, plus work output of the high pressure turbine. This is your energy equation. Okay. So these all details of enthalpies are given in the table of problem itself. Okay. So from that we are calculating our work output. Okay. So now what is asking over here? The problem D is asking you to calculate efficiency. Okay. Efficiency. What is the net output work you are getting? This plus this. Okay. That is coming around 40. Okay. But what is the equivalent of energy we have given? Heat energy. Oh, sorry. Here, the problem it is given. Okay. The heat exchanger in the reactor supplied 157 megawatts. Okay. So that is Q in. So in our this chapter itself, where when we are defining our first law of thermodynamics, there we have defined our efficiencies also. Yes, efficiency equal to work output divided by heat input. Is it? This is the work output, this is the heat input. So the total system of this much only. Okay. This is like 0.26 efficiency. Okay. So this is about problem number 5. We are not going to solve this particular thing. What is that? Engineering equation solver. This tutorial is completed. Tomorrow 9 to 11. So let us discuss about second law of thermodynamics, which is very important. Okay. Thank you. Thanks a lot. After this class itself, I am posting this presentation, this tutorial presentation, as well as code whatever we have written, that engineering equation solver. That code actually I have not saved. Okay, I was deleting one by one. Yes, while solving. So again, I have to write the code and then I'll send you. That will take 1 hour for me. Now 12 to 1 I have another class. Evening sometime I'll upload your this ES code. Okay. Anyhow, this tutorial presentation I'll upload now. Thank you. Thanks a lot. Do you have any questions? If no questions, okay. Thank you. Thank you very much.
Thank you, sir.
Thank you, sir.